All right, so today we're going to learn about exponential functions. You've already learned your exponent rules. Now we're going to actually take what we know about exponents, we're going to kind of apply it. You'll need the sheet of paper that you picked up. You'll need a sheet of paper, just a blank sheet of paper. You'll need the recording sheet just so you can kind of record what's happening, your calculator and a pencil. All right, so when you look at your sheet of paper, just look at the one piece of paper that you picked up. How many layers do you have? Hopefully what you're saying is that you have one sheet of paper. You have one layer. This sheet of paper that you have is one layer big. Okay? If I fold it in half, how many layers do I have now? Well, if I fold it in half, I have 2 layers. So now I've got 2 layers. Okay? All right. If I fold it in half again, now I've got 1, 2. So I started with 1. Now I have 2, and now I've got, well, I'm sorry, that's not 3. What am I doing? 4 layers, okay? So record what you've seen so far. So when I had no folds, when I hadn't folded, I had 1 layer. When I had 1 fold, there were 2 layers. When I had 2 folds, there were 4 layers, okay? Now, if we look at just the process column, how many sheets of paper did we use? Okay, well, we started with 1 sheet of paper. And what happened to the number of layers every time I folded it? Well, they doubled, which means they were times 2. And how many times did we fold the paper? Well, this time we folded it twice. Okay, so if we think about what that's going to look like, okay, I started with 1 and I doubled it. Okay, so I look at this one, I started with 1 sheet and then I doubled it. Then I took that sheet that I had doubled, okay, I doubled that. Okay, so I started with 1, then I took that 1 and I doubled it, then I took that 1 that was doubled, I doubled it. Okay, so when I look at that, if instead of writing that like we wrote it, if I write it with exponents, I see that the first one I wrote, I doubled it no times. The second one I doubled 1 time. The first one I doubled 2 times. Okay, so 1 was the number of sheets of paper, 2 was what happened after each fold, 0 was the number of folds. The second one, 1 was the number of sheets of paper, 2 is what happens, but then 1 was the number of folds. For the next one, 2 was the number of folds. This is an exponential function. So if I look at this, the format that we use is y equals a times b to dx. That's kind of like the parent function of exponential functions. A right here tells me how many sheets, in this situation, tells me how many sheets of paper I have, what I start with. B tells me the number of layers after each fold. And that's like, in our case, it's doubled. So I'm doubling every time. So that's how much it's changing by. And x tells me how many folds I have. The reason we have x as our exponent is because we don't know how many times we're going to fold it. That tells me how many times I have to double or how many times I have to triple. Okay, so that's what makes exponential functions different, is that the x, instead of being like after a coefficient, the x is the exponent, which is why we call them exponential functions. So let's continue folding this paper. If I fold it 3 times, so on my 3rd fold, that's going to be 1 fold doubled 3 times, which should be 8. My 4th is going to be 1 fold doubled 4 times, which is 16. It's really hard to write with this pen, y'all. My next one is going to be 5 folds, which is 1 times doubled 5 times, which is going to be 32. Okay, so we could keep on going, but let's be honest, it's probably getting pretty tough to fold this paper at this point. So when we think about what this means, okay, my initial value, so I start with 1 because I have 1 piece of paper in this case. So this is my starting value. This number here tells me how much I'm growing by. So I'm doubling, so it's times 2. If it was tripling each time, if somehow I was tripling the paper, like folding it like 3 times, folding it twice to make 3 layers, then I would do 3 to the x. And x tells me how many times I fold it. I don't know how many times I'm going to fold it. That's what I know what I'm going to start with. I know how many times, what it's going to happen. I know I'm going to double it, but I don't know how many times I'm going to fold it, which is why my unknown is the exponent. The exponent tells me how many times I have to double. And since that's what I don't know how many times I'm going to do, that's why this is my variable. And that's what makes exponential functions different, is that the variable is in the exponent position. So if I put these in my calculator, if I go to Stat, Edit, and enter the points, you should see that it almost looks like half a parabola. When you just look at these points, it almost looks like half a parabola. Let's put that function in the calculator, that one that we saw, and I want you to confirm that you see this same graph that I do. And so put the points in and put the function in, and we'll talk about what it looks like after that. Okay, so does it look like a parabola now? Am I continuing up here? No, I'm not. No, what I'm doing now is it's kind of it looks like it's getting closer and closer and closer to 0. All right? So it kind of seems like a fat parabola, but it's not. Exponential functions are not fat parabolas. They look different. And when I look at the table, what I notice is that if you notice, it gets big really fast. I start with one layer of paper, and after folding it 10 times, there are over 1,000 layers of paper. Exponential growth when things grow exponentially, they grow faster and faster and faster and faster. Okay, so what does X represent? So hopefully what you're saying is X represents the number of times I folded my paper. Okay, what does Y represent? Well, Y represents the number of layers of paper I have. Okay, Y is the number of layers. After I fold it one time, I've got 2 layers. After I fold it 5 times, I've got 32 layers. What does the Y-intercept tell me? And that Y-intercept is right here. What does the Y-intercept tell me? Okay, the Y-intercept tells me how many layers, like how much I started with. Did I start with 1 piece of paper or 2 or 20? What did I start with? Okay, now I can use this also to give me information about how many folds or how many layers. So after 7 folds, I have 128 layers. After 512 layers means I must have folded it 9 times. As my X values increase, what's happening to my Y values? Are they going up or down? They're going up and fast. So how would this change if I started with 2 sheets of paper instead of 1? What would happen instead? What do you think? Well, if we look at y2, so this is my new function right here, 2 times 2 to the x. When I look at this, if you look at the graph, doesn't it look like it's going up even faster than the other one was? It's going up even faster. Okay, and if we look at so next we'll look at the table. When we look at the table, we see that everything in y2 is double what's in y1, because instead of starting with 1 sheet of paper, I'm starting with 2 sheets of paper. So those 2 sheets of paper are each going to be, so instead of starting with 1 and doubling to 2, or instead of starting with 1 sheet and doubling to 2, I start with 1 fold makes me go to 4 because I'm taking 2 sheets and folding them in half. So it's going to make everything twice as big. So it's going to go up twice as fast. So how are these functions different? Well, how are they the same? What's the same about them? What's the same about them is this part, okay? My growth rate is the same, which is this B value, which is my rate of growth. They're growing by the same amount. But what's different? What's different is what I started with, okay? In the first equation, I started with 1 sheet of paper. In the second one, I started with 2. So since my rate of growth, is bigger than 1, my function is growing. My data is growing. Because if it's bigger than 1, it's getting bigger. Okay? Now, let's think about this a different way. So now, instead of folding the paper and seeing how many layers I've got, we're going to see how big each layer is. So when I folded my piece of paper, I split the paper into regions that are bounded by the fold line. So when I took this first one, I have 1 whole piece of paper. When I fold it in half, each of the little spaces are half as big. If I fold it again, I'm a fourth as big. Okay, so now instead of us looking at how many layers I've got, I'm looking at how big the layers are. So if I look at this one, and we're just going to go straight to the exponential notation. But if I look at this first time, I had my one layer of paper. It's growing, or in this case, getting smaller by half, and I didn't fold it at all. So remember, anything raised to the 0 power is 1. 1 times 1 is 1. Well, now when I fold it one time, I take that one sheet of paper, I fold it in half once, and now the fraction, the paper, each piece is half as big. If I fold it twice, okay, I'm going to have it half twice. So half times half is 1/4. Boy, it's tough to write with this. Okay, if I fill out this entire table, what I'm going to see is 1 times half is half, half times half is a fourth, times a half is an eighth, times a half is a 16th, times half is a 32nd, times half is 64th. You see where I'm getting at. So in this case, this is my new exponential function. Okay, and when I look at this graph, you don't need to click anything. Instead of going, so the other one went up like that, kind of like a fat parabola, like, so there was my fat parabola, well, except it kind of went like this. Let me erase that. Here's my fat parabola right here. Well, it's not a fat parabola, but it kind of ended up going like this. Okay, now it's going down and getting closer to 0. Now, question, will it ever reach 0? Let's talk about that for a moment. Okay, it's not going to reach 0 because if I keep folding 1/64th, if I fold that in half, it's going to be 128th. I fold that in half, it's 1/256th. It'll keep getting smaller and smaller. I mean, theoretically, okay, practically, I mean, there's only so far I can fold this before it gets all crazy looking. But like, if I had precision tools, precision folding tools that were capable of continually folding and folding and folding, I would be able to keep on folding and I would never run out of paper. So it would approach 0, but it would never actually hit 0. We're going to talk about that more a little bit later. How is this different from the last one we did? Well, hopefully what you're saying is that we're getting smaller instead of bigger. So in this case, if I look at this, okay, the first function, how are they the same? What's the same about them? Well, they both start with one sheet of paper and they both have x in the exponent position. Okay, but what's different is that on this one, on the first one, my exponent, my growth rate is bigger than 1, and on this one, my growth rate is less than 1. Okay, now if you notice right here, it says between 0 and 1. What would it mean if I had 0 growth rate? Okay, 1 times 0 to the 0, well, we can't do that, but let's say 0 to the 1. Well, that's 1 times 1. 1 times 0 to the 2. Well, I got no growth. 1 times 0 to the 3. I got no growth. I have no growth. So I can't have a growth rate of 0 because then I'm not growing. I have to be growing. And we're not going to have negative growth rate because what even is that? Okay? So we look at stuff as being either bigger than 1 or less than 1, but we can't go below 0 and we can't go negative. Okay? So if I put this into my calculator and I go to the table, I'm going to see a graph that looks like this. If I look at this, what's happening to my y values as my x goes up? As my x gets bigger, my y values are getting smaller. And you see this down here? A lot of you guys are like, what does this e mean? It's scientific notation. So the way that will be written in scientific notation is 9.8 times 10 to the negative 4. But what that means is the number has gotten so small that my calculator can't display it anymore. In this little column, my calculator can't display it anymore. So the numbers are getting smaller and smaller and smaller. And if you keep scrolling, that E is going to get bigger and bigger and bigger because the numbers are going to be so impossible to display. So for exponential functions, the rate of change is constant by multiplying. So what does that mean? That means so instead of going 1 plus 1 is 2 plus 1 is, nope, I have to multiply. So 1 plus 1 is 2, well, I'm sorry, 1 times 2 is 2, times 2 is 4, times 2 is 8. So I'm multiplying to get from row to row instead of adding like we've been doing up until now. Okay, for this one, same thing. I'm multiplying by half. And you can put these values in your calculator and see that that's exactly what I'm doing. Okay, so with exponential functions, instead of increasing by addition, we increase by multiplication. Okay, so again, all of this to say, the last thing I want you to remember, exponential means I have a constant change by multiplication. So in my table, my delta y is going to be multiplying instead of adding. So if my rate of change is increasing, meaning it's bigger than 1, I have exponential growth. If my rate of change is decreasing, which means it's less than 1, between 0 and 1, it's going to be exponential decay. We're going to talk more about this. We're going to do a little bit of practice, and we're going to talk more about this. We're going to get into a lot more detail. This is just kind of an intro lesson. We're going to get into a lot more detail about exponential growth and decay tomorrow.